In this video, we're going to practice finding a few potential differences between various reducing and oxidizing agents. To start with, let's look at this one. Iron 2 plus going to iron 3 plus, and silver plus going to silver solid. Well, our iron is losing one electron, so our oxidation is our Fe2 plus aqueous going to Fe3 plus aqueous. And our reduction is our silver plus aqueous going to silver solid. Our goal is to find E0 of the cell. For this, I need to go look up those potentials. Our case here, if we go back and look at our table, I can find a silver plus to silver solid at plus 0.8. And I can find an iron 3 going to iron 2 at plus 0.77. So the silver conversion is 0.8 and the iron conversion is 0.77. Back to our reaction, however, our iron's in the wrong direction. So instead of plus 0.77, this one would be minus 0.77. The data table had iron 3 plus going to iron 2 plus with a positive 7.7. But our reaction needs it the other way around, so we're going to flip the sign. Our silver, however, is written just as the table was written. Oxidized form going to reduced form. That was plus 0.80. Once using the data from the table, we can use the silver as was. We can flip the iron because our reaction has it going the other direction. I can then sum these two for 0.03 volts. 0.8 plus negative 0.77 is 0.03. This has a very weak voltage. If you think about why for a second, silver does like electrons. It's a noble metal. It tends to not oxidize readily in that environment, so you can actually find native silver on Earth. It's possible to keep it as just silver solid pretty easily because it doesn't want to give up electrons to the world around it very much. Well, iron does readily oxidize, but it's already down 2 electrons. Going to a third, neutral iron would have surely given up an electron to silver plus, no problem. But already having lost 2 and giving up a third is much more difficult. The more positive the ion, the harder it is to remove the next electron. Think back to ionization energy. It just becomes more and more difficult. And so by the time we're removing the third electron from iron, it wants it just about as much as silver wants that first one back. So there's very little difference in the potential between them. Let's compare that then to what if it was iron metal? Once we have Fe solid and silver plus aqueous going to Fe2 plus and silver solid. And we'll need 2 of each of these. Well, that changes our oxidation a little bit. Now it's iron solid going to iron 2 plus and 2 electrons. Reduction didn't alter here. It's still silver plus going to silver solid. And I'd need 1 electron. I'd need to multiply this whole thing by 2, but that doesn't affect our voltage differences. Well, to balance the reaction, we may need it overall. The voltage won't be affected by that multiplying because the voltage is joules per coulomb. Double your charge, you'll double your joules, your voltage will stay the same. So I need to go back and look for these again. We already know it for the silver. It's plus 0.80, but we need it now for the iron. If we jump back to our table, we can find Fe2 plus 2 electrons go to Fe solid at negative 0.44. We'll flip it around because we had the iron solid. This will be plus 0.44 for the reverse reaction. So back down here at the reverse reaction, this is plus 0.44. If we then add these together, we'll get 1.24 volts. Why does this one have such a larger potential? Well, because now we're removing electrons from a neutral iron to make iron 2+. We're taking those first two off of something that is already full up. This is much easier than taking off something that's already missing 2. And so as a result, they more freely come off the iron solid. The iron solid is higher in potential than the iron 2+, and so we have a greater distance to go to get down to the silver, and we see that in our voltage.